It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we're going to talk about two types of waves as well as wave interference. So what happens when waves interact with each other? So the two types of waves we're going to talk about are transverse and longitudinal. So let's make a chart to separate the two. So on the left side we have transverse, and on the right side we'll have longitudinal. A transverse wave is the sine wave that we looked at yesterday. So we're just going to draw a sine wave to represent that. And we'll look at properties of each. One thing that we observed yesterday was if we had a particle or a mass sitting on the wave, we saw that in this instance the particle is going to move upwards. If we move it to the left side, we're going to look at what's approaching P if the wave is moving to the right. And what's approaching P on the left side is the downward aspect, so P is going to move downwards. Notice that the wave is moving towards the right and P is moving up and down. So we can say that the mass on the wave moves perpendicular to the direction of the wave motion. So the mass moves perpendicular to direction of wave. We also saw from the previous video that the wave only transfers energy and momentum. So a transverse wave only transfers energy and momentum. We'll use lowercase p for that. Let's also write down that mass is not transferred. Oops. Different color. Mass is not transferred. Now there's multiple waves, forms of waves that are transverse waves. In this class we're going to look at electromagnetic waves that are transverse waves. An electromagnetic wave is also a light wave. Now, if it's an electromagnetic wave, then it's not going to require a medium to travel in. So it does not require a medium. And a medium is just a material that it's traveling through. So an electromagnetic wave can travel through air, it could travel through glass, but it doesn't necessarily need a medium, so it could travel in a vacuum. Now just to be clear, this is just for electromagnetic waves that don't require a vacuum. So if we're looking at an ocean wave, which is a transverse wave, that does require a medium. Okay, now let's look at a longitudinal wave. Imagine you're holding a slinky and just moving it up and down. That is going to create a transverse wave. But to create a longitudinal wave, what you'll want to do is take the slinky, grab all the coils, or as many as you can, and release it, and you'll see the slinky move back and forth. So there's going to be areas where the slinky is bunched up, where you have all the coils, and then areas where there's not a lot of coils, and then so on and so forth. So lots of coils. We'll do one more, just a little bit. We can also imagine that these are air particles. And we could see or imagine that the slinky is going to move back and forth from the left to the right. The areas that are close together of the slinky, the coils, that's called areas of compression. And the spots where they aren't as close or bunched up is called rarefaction. We'll look at the wavelength of a longitudinal wave in the next video. For now, let's imagine that we take a particle, and we put it somewhere on a compression area. We'll label it point P. And this particle is going to move left and right, or back and forth. So in this case, the particle is going to move parallel to the direction of the wave motion. So even though the mass isn't transferred, it'll still move along with the wave, but it's going to end up in the same exact spot that it started from. So the mass moves parallel to direction of wave. And just like a transverse wave, a longitudinal wave only transfers energy and momentum. And also, just like a transverse wave, mass is not transferred for a longitudinal. So mass is not transferred. No matter what type of longitudinal wave we're looking at, they all require a medium to travel within. So it requires a medium. So it has to have some material for it to travel. And then lastly, the types of longitudinal waves that we're going to look at are sound waves in this class. So a sound wave is a longitudinal wave. So those are the two types of waves we'll be discussing in physics. What we're going to look at next is interference of waves. So we're going to look at constructive interference and destructive interference. To make things easier, we're going to look at transverse waves. However, the properties we see are applicable for both transverse and longitudinal. So if we could look at faites, and what we're going to do is send a wave pulse and we'll watch the wave. It's going to hit a loose end, and notice when it bounces back on a loose end, something that's able to move, it bounces back on the same side. If we send a wave on a fixed end, so something that's sturdy and won't move, as the wave approaches that, it's now going to reflect and go back on the opposite side. And what we're going to do right now is send another wave going to the right. And let's watch what happens when the first wave and the second wave interfere with each other when they're traveling towards each other. Notice their amplitude right now. Once they meet, notice that the amplitude got larger. So they increased in size when they interfered with each other. Afterwards, what's going to happen is the wave that was moving to the right will continue moving to the right, and the wave that was moving to the left will continue moving to the left. So let's draw that to get a good idea of what's happening step by step. So for constructive interference, before they interfere, we have one wave going to the right. Let's call that wave 1. And a second wave going to the left. We'll call that wave 2. And what happens when they interfere? During the interference, the amplitude is going to increase. So now we're going to have a larger wave. We'll call it 1 plus 2. As we saw, although it's difficult to see, but afterwards, they pretend that nothing happened. So after they interfere, wave 1 will keep moving to the right until it hits something, and wave 2 will keep on moving to the left. And that's constructive interference, where the amplitude increases. So let's now look at destructive interference. Let's look at a similar scenario, except this time, one wave will have a negative amplitude. That one will be moving to the right. And another wave will have a positive amplitude. That wave will be moving to the left. So we're going to send one pulse. We'll send another one. And we're going to wait for those two waves. Right now we have constructive interference. We're going to wait for one of the waves to bounce off of the left end and reverse its amplitude. Okay, so now we have the wave moving to the left is on the positive side. The wave moving to the right is on the negative side. I'm going to look at this step by step because it happens quickly. So when the waves interfere with each other, watch the crests. Notice now that they have destructive interference where the amplitude decreases. Looks like it disappears. And then afterwards, they're going to continue moving in the same directions as they were before. So the negative amplitude wave is now still moving to the right and on the bottom. The positive amplitude wave is still moving to the left and on the top. I'm going to let this play for a little bit, back and forth, so you can see both constructive and destructive interference. Alright, so let's draw a picture of destructive interference. So before we have, we'll say, a wave with a positive amplitude moving to the right, and a wave with a negative amplitude. I'm going to make it slightly smaller than the first one, moving to the left. So when they interfere during the interference, because wave 1 and 2 aren't the same amplitudes, the wave won't completely disappear, but it will get smaller. So all we're going to do is subtract wave 1 minus wave 2, and that's going to give us a wave with a smaller amplitude on the positive side. So that's 1 minus 2. If they're the same amplitudes, then the wave would disappear momentarily. If 2 had a greater amplitude, then the wave would be somewhere on the bottom. Okay, and then afterwards, they pretend nothing happened. So wave 2 is still on the negative side, moving towards the left. I think I switched the color, sorry. And wave 1 is still on the positive side, moving towards the right. Oops, bigger amplitude. So destructive interference, the amplitude decreases. Constructive interference, the amplitude increases. The last type of interference we're going to look at is called a standing wave. So we're going to use another simulation to help us visualize what's happening. So here we have two waves, an orange one and a blue one. So imagine the orange wave is moving towards the right, it hits a wall, and then the blue wave is the reflected wave. If we look at the ends of either wave, so if we look at the end of the orange and blue wave on the left side, that's a form of destructive interference. The same thing of the blue and orange wave on the right side, also destructive interference. When we press play, in slow motion, we'll put it in real time, notice that the orange and blue waves are always parts of destructive interference, and they're always going to add up to 0 because they're the same amplitudes. If we look in the middle of the wave, that's where we have constructive interference. Their amplitudes are both either negative right now or both positive, so they're constantly going to add up to each other. So if we look at the interference of these waves, we get this thick green line that shows where there's constructive and destructive interference. What we see, if we get rid of the blue and the orange, and we'll put it in fast motion, is a wave that appears to be standing still. Now if we increase the frequency of the waves, we'll get rid of the blue one, so if we make this move faster, if we move our hand faster, then what we're going to get is more periods of constructive and destructive interference, and what we see is this green line. And then if we move our hand back and forth even faster, we'll get more periods of constructive and destructive interference. Again, this is what we see. The wave appears to be standing still and just flipping back and forth, but in reality it's the two waves that are interfering with each other. And we can keep doing this until we get more and more harmonics, as they're called, or more and more periods of constructive and destructive interference. So all a standing wave is it's a wave that appears to be standing still based on two waves interfering with each other as they move back and forth. So let's define what a standing wave is, and we'll also talk about the parts where we have maximum amplitudes, or the crests, as well as the spots where there's complete destructive interference, where it looks like it's not moving at all. Let's see. Okay, so a standing wave is when we have two waves of equal amplitude and frequency traveling in opposite directions and appear to be standing still due to constructive that's where we'll get the maximum amplitudes, and destructive, where the waves cancel out, interference. So let's draw a standing wave, or as best as I can at least. So I'll draw one wave going to the right. We'll try and keep the frequency the same in amplitude. And then that's going to bounce off a wall and reverse its amplitude and start going to the left. And as we could see, there's going to be periods of constructive and destructive interference. Now if this were our standing wave, where we get the maximum amplitudes, or the crests, those are called our antinodes. Sorry, I should have drawn this lower. And then the periods where we have destructive interference, where the wave is not moving at all, or where the amplitudes cancel out, those are called the nodes. So in this case, if we were to count the nodes and antinodes, this specific standing wave has 5 nodes, and then 4 antinodes. There's always going to be one less antinode than nodes. And for the nodes, all we want to do is just count the crests. So there's 4 crests in this case. And that's it. If you found this video useful, please like and subscribe. And I'll see you next time. See ya.